He's also a Purdue alum from 1983, civil engineering, hydraulics engineering area, gone on to fame globally. As he said, don't read my resume, but I'll just mention that he's a member of the U.S. Academy of Science, member of the U.S. National Academy of Sciences, as well as Engineering, and Swedish Academy. So, among other many honors that he will not let me read. But I also want to take this moment to recognize Chris Burke, who is in the room, and he'll be the second speaker. Chris Burke and Andrea were classmates in 1983. And two professors who taught them are in the room. Jacques Delors, who's now emeritus professor. Thank you, Jacques. Good morning. And Kumara Sinha, right behind him, who is still an active professor. Last night he reminded me he still got it, and I'm sure he does. And so does Jacques. So, anyway, so I'm glad to have these people. I'm glad to have all of you present here for this occasion. I'll ask Andrea, with that brief introduction, Andrea, to please come give us his presentation. He will be followed by Chris Burke.
Thanks so much. So it's a great pleasure to be here, of course. And to actually meet so many friends or professors. And as whoever knows me knows that to me, this really means a lot. Purdue means a lot. And I've had a wonderful education in this place. And I should put this. I think in my hand and let's see. So without further ado, I didn't prepare. I should have probably dug out some pictures when Chris and I were students here, but I think just for the moment I'll be talking about, even a relatively, not really technical talk, but an outline of what I think will be an important somewhat topic in the future of hydraulic engineering in particular. And I underline engineering because what I do think is that what is really missing in the general debate of the critical development of, say, economic thinking or development thinking versus environmental thinking, what is really the missing point is a proper engineering for a proper hydraulic engineering for a proper sustainability concept. So it's the title of my talk is the title. It's a bit abused because I've been using it quite a lot, but I have, there's a book now is going to be out pretty soon, published by Cambridge University Press, which has the same title, the subtitle Species, Populations and Pathogens, because as I will try to show in this talk, and there is a conceptual thread that joins all of them. And see the guy that you see here, the little guy, the young guy from Bangladesh, was drinking the water of the mighty waters of the Meghna River, which is a tributary to the Ganges, because it was going to show me that, like in Jon Snow's time, the Victorian medical doctor that convinced people that cholera was not brought by miasms, as they call it, in the air, but it was something that some bug that were sticking to the waters, to drinking waters in particular. The guy said, no, it's not possible, so he drank the water. What happens is that this place, where we did field work for quite a bit of time, is like 200 meters downstream of a hospital, the largest diarrheal disease hospital in the world, which is in Matlab in Bangladesh, as a subsidiary of the Dhaka Institute for Diarrheal Diseases, which is the largest in the world, where actually cholera, in evolutionary sense, developed first, and then irradiated worldwide. Now, why this is important to me? Because if you think of it, the guy is nuts. But you think about the odds, but you can't predict whether or not the guy catches cholera, you're humbled. Because what happens, you see, you catch cholera if you ingest a dose. It's a dose-dependent number of bacteria. And the chances that you can predict with a reasonably small uncertainty, something which comes from a point injection in a specific point in space and in time, is pretty low. So the weakness of our capability to predict, in many a case, is a permanent liability to our possibility to push a price tag, in fact, on the ecosystem services, in this case, drinking water. This is a key point of the reflections that I will be putting together today. Let me put this here. This one. So just a little bit of a general background and what is the context here? The context is that of development thinking versus environmental thinking. What happens is that in reality, Simply, economic indicators like the gross domestic product do not give a full idea of the total value of the environmental, the state, what is at stake actually. If you wipe out the wetland to make way for a commercial center, certainly the following years you will see the GDP of the area, whatever measure of economic indicator, you will see the effect, the good effects, employment and whatever of the commercial center. But you don't see the cost of the environmental services you lose, largely because you cannot put a price tag on those services. So we've been on continuously under what, so as to say, the spell of so-called Kuznets curves. Kuznets was the expatriate economist who settled at Harvard, but essentially based on empirical evidence after World War II data, he was contending that with the increasing of the GDP, inequalities would be reduced. Now, a revision substantially denies that. It's not true that it's simply a richer country in terms of GDP. It's also a more equal country. So the true concept of sustainability is something which should be able to evaluate the value, the depreciation of the natural capital, because no economy can be made to thrive by mining natural capital. So why river networks are central to the reflection that we had in this case? Why are they important in a quantitative evaluation of ecosystem services? So what I've been talking about here is something which is narrow and yet somewhat, hopefully, irradiating a number of structures, embodying what is now seen as an important chapter of ecohydrology, that is the water controls on living communities of biota. So I'll be talking about a few issues based on laboratory, field, and theoretical work that we've been carrying out, my group has been carried out in these years. Ideally, as hydrology is about floods, droughts, and the fair distribution of water, I'm interested in the true meaning of fair distribution of water. And there's a particularly troubling example, which is there's a debilitating disease called schistosomiasis or billiard soles, which is not a fatal disease, it's a largely neglected disease, which essentially is a macroparasitic disease. I could bore you to death with why water has to. We are interested in waterborne, water-based, or water-related disease, that is something in which at least either the host or the parasite live for a part of its cycle at least within water, so there's a control of some kind of that. That's why we are relevant in this debate and why I believe that this is relevant to hydraulic engineering. But in the case of macroparasites, it's a fluke, it's a worm, it's a round worm that gets into the skin, penetrates into the skin just simply by contact with water when it's infested. It has an intermediate host, which is a particular kind of freshwater snail called Bulinus, which, and that's an interesting game to be played about the abundance of the intermediate host, but just a few snails can spit out tens of thousands of parasites. So the probability of somebody putting his or her hands in the water and getting the disease is so high that my graduate student that was doing field work in Burkina Faso, where you've seen the picture before, just only once dropped the gloves because he dropped scissors, just put the hands to pick up the scissors and got the disease. What is a shame is that by taking one pill of praziquantel, you kill the parasite, but it doesn't give any immunity. So anytime you put your hands again into water, you get it again. It's a debilitating disease. It's a poverty-reinforcing disease. It's a learning impairment that is generated in particular important times. So there is a huge cost, which is very hard to put a price tag on. Now, what happens in Burkina Faso, that something like 1,500 small dams have been constructed, like the ones you've seen before, that you see here, temporary ponds, you store the water, and you have irrigation canals that distribute and ameliorate significantly the agriculture in Burkina Faso. Now, certainly, you've seen in the GDP of Burkina Faso the increase, the benefits brought in by agriculture, improved agriculture, very much so. But nowhere to be seen is the cost of increased disease, which is generated by the expanding range of intermediate hosts. And the prevalence of the disease in the young kids that you can't pretend. I took a picture here with my phone. It was a temporary pond. All the kids out of school were just jumping in the water in there. It's highly seasonal. It's a particular hydrologic regime of sub-Saharan Africa. So what happens is that in a place in which it's also an ad, right? But something is priceless. If something is priceless, it's worth nothing in academic terms.
and to be able to put a price tag on the service, like in this case, material immaterial values. Can you GDP increase versus the incidence of disease and the learning impairment, which is hard to quantify. Unless we do that in a quantitative manner, what I call a proper engineering of proper sustainability, if it includes natural capitals, we won't really progress. And so why are river networks? This is not a river network, it's a trick. This is a tidal network from my birthplace. It's from the lagoon of Venice, where I was born, and to which I'm much touched. But the message comes clear. You see signs of the natural environment here. You see those white things are more or less traditional ways of doing fishing. And there is a co-evolution of the built and the natural environment, you see. Why are the networks are so important? Now, questions that you may want to ask that will begin to be important is, will large-scale water management plans include biodiversity protection in the future? Because they do not now, and they should. Is a river network a template for the spreading of deadly or debilitating disease? Or is there any other network that just by looking at that you would know the pattern of the spread of disease? To name just a few. Other, for the matter, other questions of this type. And why we move from that? Because we know a lot about how to render. This looks like a photograph, and it's not. It's a digital terrain map. Now you probably gathered that from the talk of perhaps Jim and Gianluca, for sure, later on. We can describe the geometry of nature, of scales that go from the stamp size, filtering for the vegetation properly, to the size of tens of thousands of kilometers. The one, in fact, in the debate over self-organization and the shapes that inevitable forms in the dynamics of nature became important, and that hydrology became center field, because very hardly other data sets worldwide are so accurate, so verifiable by ground truthing like ours. And we have lots of tools like artificial networks, like in this case, something that we've been working for a long, long time, which can generate statistically identical replicas of very complex patterns of this kind. Let's see why this supposedly matter for that. So essentially what we have, my point of contention is that if you constrain ecological interactions by the shape, by directional dispersal, you already have cut out a large part of the uncertainty in our predicted patterns. So the environmental substrate or matrix, if you want it, is a system where you have nodes, where you have reactions that could be biological, that could be physical, that could be chemical, in fact, and connections. And connections could be real connections like a river, pathogen flowing through the place, or it could be different type of network. A susceptible guy to a disease moves to a wrong place, drinks the wrong water, and gets back. He brings back the disease. Now, this is a network per se, and when we have a state variable, which is the concentration of pathogens, would be affected by that. So I'm not, if anybody's interested, especially the young guys, we'd be delighted to address it, but there's a machinery in the oriented graph theory and of all kinds in epidemiology, effective hydrologic transport, which plays a practical role. But what I want to do, and that's exactly the subject of a book which is about to appear. But what I want you to, I know the skepticism in many ecological circles about the assumptions I'm going to discuss now. But let me see if you can see what's the general pattern in there. What's the general pattern of engineering? General pattern of engineering would be, let's develop an abstract model, rough as it is, understood in full, to move on to generalize on places. But in physics it was the norm. Spin glasses being used to do something which was nothing but a spin yes or no, switched on or switched off, to understand how the matter made actually. But let me show you the examples, which is an easy one, which was done in social science. It's called a voter model. Now in Europe, the discussion about who should be deciding, it's a very hot issue, and it's part of that perhaps migration is also a big hot political issue. But keep in mind the following. I'm talking about a model of spatial ecology, in the sense of Tilman in particular, extended to embed a particular substrate. So essentially what I have is that I have places, you see here, yes, in which you have nodes, and your nearest neighbor with which you interact, in one case is the so-called von Neumann neighborhood. It is each of the nearest neighbors is a guy you can interact with. In a directional dispersal setting, same number of nodes, the connections are different. This guy and this guy seem to be close, but they are not, because they are connected by a path, which is not nearest neighbors. So essentially, you can tell the system whether you'll be choosing between the guys that are near you in a proper sense, whether this is what happening or not. So what happens if we follow it? Let's take two systems of the kind. It's called a voter model, because like, suppose you have an initial distribution of colors that have political opinions or species. Each node is one opinion, in this case, like each node will be a species that you have in the system. So you have an initial condition, and you, at random, you choose a side, and you kill whoever was in there. You have to replace it. You may replace it with the majority of the colors you have in your nearest neighbors, properly defined. It is like, I have no stronger political opinion, but I have two guys that think red, I have two guys, one blue and red, so I would take that in the immediate neighborhood. And that's it. You keep going. Now, if you do that, the asymptotic state, if you do nothing else, will be obviously the one in which you say that the initial advantage will be the one that you carried out until the end. In the end, it would be a single political opinion, the one that was in the majority at the beginning. So, a process which is completely dominated by the initial condition, not the property. But in every, say, 10 to the minus, 10 to the 5 trials, etc., rather than killing the thing and replacing it with the neighbors, you introduce a new species. This is called the immigration, which is in ecology is called the diversification rate. The picture changes completely. And you get to a steady state which is highly non-trivial. But what I wanted to show you here, that the only difference between the two graphs is simply the definition of neighborhood. In one case, you are exposed to interaction with the nearest neighbors, openly. In some cases, you shield it. Because, for instance, you have a source place, you have only one neighbor on. Now, if you do take measures, which is called abundance of gamma diversity, or whatever you want to call it in this case, what happens is that even the visual impression, the colors, the boundaries in one case are more jagged. In the case, they are more rounded. But even what's most significant, in the end, even the abundance is completely different. And the only ingredient which is different in this case, it's a highly theoretical model, is the definition of neighborhood. In one case, it's a network. It's a network given by something which is a substrate for interaction, like if it was a spanning river network would be given. Now, why this is interesting? This is interesting because the result resists several layers of generalization. This is individual-based and completely neutral, which is anathema to some ecological circles. But it's very interesting. The neutral model of biodiversity by Hubble is an interesting step forward, which you can exploit in full to get hints, analytical solutions, etc. Why does it resist? Because in a node you may have not simply an individual, but a population, or you may have a community. So you have meta-community models in this case. You may relax the assumption they're going to be only the immediate near neighbors, and you will have what is called a kernel for the reaction. That is, you have a certain radius of influence for which you can draw the political opinion will replace, or the species will replace your one. Or it could be the mean field, as you call it, that is, you can bring it from anywhere within probability. And what happens if you do this? You find that the topology of the substrate is a jargon, but the shape of which you are taking the definition of neighborhood carries over. Mean field, one-dimensional, two-dimensional, three-dimensional, it's a completely different thing. So you go down to the field, you may actually find, but I'm not insisting on that because otherwise Anamika will kill me because when time comes I'll be stopping. So no ecologist or biologist will be interested in trying to see whether in living communities this result would hold. So I set up, thanks to the resources that Switzerland allows you to mobilize, to set up my own wetland. So what we did was to prepare something like Sky Networks, designed, as you see, very artisan-like thing. So we had like a lattice or a thing, and we did carry out properly dispersal experiments in a place in which, in the medium of every of those shafts, you have 21 species of protists to learn how to cultivate, etc. What I'm saying, engineers learn everything. It's biology that don't learn math. So we have an edge of advantage, guys. That's what I keep telling everyone. Long story short, you can do replicas of the system, and you see that experiment, there's nothing neutral here. There's a living community. There are bugs that are living, and in some case they compete. There's competitions, nothing that would survive in theoretical scheme. You do see that. The main message that carries out from very abstract model is verified, at least in this experimentation. So the level of biodiversity is completely different in two cases. There's nothing but keep repeating the example, having students working hard to do replicas in a proper sense. And that was, the paper became one of the 100 biology papers of the year, or whatever. The experiment was deemed a success. But then you can do better, so the level of a medium you can put in those shafts can be tuned to be river-like, meaning one of those Leopoldian relations we've been discussing yesterday at Leo's thesis presentation. That is, essentially you have that the level of a medium is proportional to the number of guys that are connected to your back. This is the structure. Is the equivalent having the habitat size depends as the hierarchical on the network shape. So you can actually have, with the total amount of medium, you can have a uniform case. You can have a case in which at random you place the same volume wherever you want, or a hierarchical system. To get what we know, that essentially something is written in the distribution of biodiversity in the river network, which allows you to be more precise. So you move on from replicas of guys this big to the Mississippi. And what happens is that, do you have any doubts that there is a connection? This is a fish diversity, LSR, means local species richness. There's a very accurate database, essentially curated by the USGS and by Bill Fagan in Maryland, actually, who's the author of the paper. And so what you see is that the map that you see on top is the map of fish species diversity. And the map you see down there is the annual average runoff production, which is something which hydrologists know well how to calculate. So it's a feature that depends on it. Now, it doesn't take a statistician to know there is a linkage, right? So the idea is that models like these, like a neutron model, in which in one case you put the description of what we know better than anybody, how to characterize the geomorphology of the river network, has a major say. So you can predict, you can go along and predict the average local species reaches along the topological distance, say from New Orleans to the sources. Or for this, by the same token, you can study, and these are tools of engineering. I could test interested students for a long time. Right? You can study the stability. So in ecological dynamics of coupled systems, this was like a salamander. I wish we could do something for the cane toad that we started seeing about yesterday in the interesting presentation that they made for us. But the idea is that in the ecological dynamics, you may have a state of equilibrium. That is, nothing changes. That is like a steady state abundance of a species. You can study its stability. That's something engineers know how to do, especially even in spatial explicit methods. You essentially take Jacobian matrices, which depends on the number of nodes and the number of coupled equations you have in the system. So you can study when they become unstable. So you may have this so-called exchange of stability. Or you may study, in this case, as you simplify a network by optimizing it, you can study a measure of the viability of a spanning network per se as a viability for population survival. It's called the metapopulation capacity, the Hanskian concept. And by the law of unintended consequences, what you have is that a network that gets simplified, like in this case, and get optimized on physical premises, actually unintendedly simplifies considerably the viability for the species. So there is some sort of a convergent thing. Is the network shape telling you something about the biodiversity of the system? Because the answer is yes. But where I think that what we do takes an edge of social and economic ethical value too, is the fact that by some strange thing, by exactly the same token, we can study how disease propagates, waterborne and water-based. So if you assume that, like in this case, nodes are human communities where a certain disease may spread, and so essentially what you do in these kind of models, you partition the population, the demography, into susceptible to the disease, infected persons, and recovered persons that can go back to, if after some acquired immunity, depending on the length of the acquired immunity, can go back to the state of susceptible. When you have a state variable that is the bacterial concentration in the water reservoir, something can be highly idealized or highly physical, like in Bangladesh, where you dig a hole, and with the clay you take out, you make a mound on which you build your house, and the hole is where you get the reservoir of water from the entire season that fills in the monsoon region. Now, so essentially what you have, the spatially explicit texture is the fact that you have human communities spread, you know where they are, and the connector for pathogen dispersal, which are waterways, which you know where they are, essentially. And so, look at the Haiti case, for instance, which I studied. I've been doing field work in there during the epidemic, so something interesting we might see, actually. It's just, Haiti is a very unfortunate case. The symbol of our responsibility is because Haiti had something like millions of cases, and Haiti had been cholera-free for about 200 years. We planted the disease with the UN Nepalese soldiers, the peacekeepers, after a disastrous earthquake that hit the poorest country in the world. And we, developed nations, planted cholera in a place in which you could safely assume that the entire population was susceptible to the disease. Isn't that a shame? So let me show you what happened starting in October 2010, a few months after the disastrous earthquake, in a place in which there's no water infrastructure, there's no sanitary infrastructure, there's no water supply system, there's no roads, there's no police. No insurance will pay you unless you go with the thing in there. And so there's a total cumulative cases reported week by week by PAHO, the Pan American Health Organization. So I'm not doing anything, I'm taking the weekly cases and plotting them together. What do you see here? You see the network. And you see the network, it's an interesting point because I haven't done anything. I just simply show what happens. And if you take the data, you also see there's food for thought for hydrologists and hydraulic engineers. Why? Because once you have the rainy season, the heavy hurricane season or whatever, what you have is that you have a revamping of the cholera cases. Largely why? Because in the system we have no sanitary infrastructure. Either have overflows or raw sewage. Not the case in Haiti, there's no sewage system to begin with. But you have washing out of open air defecation sites. You load bacterial concentration, you increase the exposure in a predictable manner, as it turns out. And so the hopes is that the tools for predicting how disease spreads, ideally to match what you see in the end, the shape of river networks, are tools of civil engineering. You talk about the digital terrain maps, you're talking about extraction of river networks, objectively manipulated, objectively extracted, so we have, as the direction of connectivity of a discharge of pathogen from place. Mind you, the biggest reservoir for a pathogen is the human being infected. Like one discharge would be millions or billions of times more than background concentration can be reached by natural surviving pathogens in the environment. And then you have mobility network on which I shall return, which is a pretty important one. So essentially what you have in every node, which is every human community, in which you have susceptibles, infected, and recovered individuals, you have a population, you assume stable demography, that is the mortality due to the cholera is relatively limited to conserved populations. You have tools to generate several variants of couple ordinary differential equations, which we can master wonderfully well. A civil engineering student at an undergraduate level using MATLAB can carry out and define the program perfectly well. And then we have like toys we play for a long time with tools in which you can even calculate analytically the speed of cholera waves. So I may show you what happens in a piano case because that matches the analytical solutions. In a highly idealized case in which you have population, uniform population in every node, which is highly unlikely, but you can calculate, you see the wave progressing in the number of cases which you have in a particular case, with a particular duration, which is set for the thing. And if you get the same total population, but you distribute the population according to a distribution, now, what is interesting is that it's absolutely fascinating why the distribution of the size of the cities is a power law anywhere in the world as soon as you take a significant sample. And there was the invisible hand that guides the fact that you do not have like a big city and a small city, but you have cities of all sizes. These are interesting questions per se, but in long story short, for us, computations are easy, but then you go to the field and you try to see what happens, and you see that this is supposed to be safe drinking water. Would that be safe drinking water? The guy handling you a bottle, keeping them with his hands and things. So, once you go to the field, you need some sort of a stochastic framework anyway, something we are equipped to do. Or when we talk about human mobility and human-to-human transmission rates, we're talking about things of this kind which I witnessed precisely. But I want to show you in particular this. You know this lady with a button on her hand? We were in an armored car because they can kill you to steal your camera, essentially that place, especially at that time at the peak of the cholera case. That lady, 10 meters away, I was already putting down thing. You know what she did? She showed the phone and got the cabbage in return. I saw it with my eyes. Now, what kind of a society is one in which the Nokia 1900 has a penetration where there's no social buying the ownership of a phone in the poorest country in the world? And it can learn and do transactions with the phone in the market of Carrefour at the heightened peak of the cholera case. And we do not have the money to put the sewage system in place in the damn place. Isn't that strange? So this is teaching us something about patterns of general nature, of which we can help actually. Why? Because what you see here, we have the capability of predicting, and what you see here is like after tools we know what to do. 2 minutes already.
2 minutes late.
It's going to be, I must keep this significant, I know I love to chat, but just wanted to give you an idea. So what it means is that then the tools we have are tools in which we can actually calibrate systems, discuss about model identification, about parameter calibration, so that's something straight for us. But you can also study the shape, essentially the eigenvector of a leading eigenvalue associated with the Jacobian of a disease-free equilibrium to see where the disease goes, and which is interesting. Or, if you please, you can also make prediction what will happen like in a few years, like generate a rainfall pattern over time. And you can put a stochastic model on how, in fact, what's the probability of the extinction of the disease. Or for that matter, if you have no rivers, like in Senegal, on which we worked, you can use phones to track mobility. In this case, it was significant because nothing could explain like the gravity of radiation models of the fact that in the Gran Bagal de Tuba, in a place in which you have like 3,000 people, you get 4 million people in sort of a religious pilgrimage. And then you have a thing in which you have, at the height case, 27,000 cases of cholera because they get back home to spread the disease, and this can predict. So I'm not talking about the fish, because one of the questions you might want to ask in this case was talking about peripheral kidney disease while I'm getting to the place, and eDNA, which is going to be a next frontier. Okay, I'm sorry. I'm supposed to go to the conclusions here. Here they are. What I'm saying is that one of the questions you may ask, okay, will iconic species like the brown trout disappear from the Alps? It's a reasonable question you may ask. And we have tools for doing that, because essentially what you have is that you can study the metapopulation of trout, brown trout, in a context in which you see what's the intermediate host for a proliferative kidney disease, for instance, which is something which is related to the habitat suitability of the river network. So, long story short, there's a coherent thread that joins species, populations, and pathogens. I won't talk about pathogens actually. I haven't talked about biological invasion, which is also an interesting one. But my conclusions are these. So you have eco-hydrological footprints of rivers as ecological corridors, quite visible in patterns of biodiversity. I have very little to talk about fish diversity, but I have several examples. And the spreading of migration of waterborne disease, like in this case epidemic cholera, but it could be endemic schisto, or could be deadly PKD in fish, in fact. What is interesting is that the network structure and the fluctuations are very much induced to be topology and the metric of the substrate you have for ecological interaction, which is the river network, something we know better than anybody. So essentially from the peaks of prevalence of waterborne or water-based disease to patterns of species abundances to the susceptibility of biological invasions, which I haven't particularly mentioned that. And the general idea of sustainability, it's all in the water, the message I have. So I think that hydrologic engineering, and it's a grateful thought to my alma mater that trained me so well here, and I'll always be grateful, is the true sustainability in the sense that we're talking about the fair distribution of water as a worthwhile goal for the next generation, is discounting the environment, putting a proper price tag based on the limited liability of the uncertainties we have in predicting, and in that way, rethinking social equality. Thank you. I'll be delighted with questions.
Floor is open.
Can I ask you, Andrea, a question? It's very nice.
Thank you.
Now, rivers, most of the rivers don't aim at the boundary of a country, political jurisdiction. And the pathogens is carrying, or whatever other thing carrying, it goes through the parts of the boundaries of countries. So what we can do, to tackle this kind of problem in its regional compacts.
Oh, okay. Well, that's...
So,
well, I'm afraid that gravity rules. And there's no way that if a political, well, some of the largest contentious issues in the Middle East, is no surprise, is the managing of the where it all began, right? The Euphrates and the and essentially the fertile percent, the waters in the Turkish part are regulated by rivers. There are significant alterations on the regime now. This has implications. Once you change the stream flow distribution, you have changed the fluvial ecosystem, stream ecosystem, whether you like it or not. You change the survival and the suitability of a pathogen, etc. All we can say is that, look, it's not for us to take a political stand. We can say, to the best of our knowledge, how the process will unfold. If you do this, it's going to be the response.
Do you have any example or any place that regional countries have made a compact to tackle this kind of problems? You know, anything of your
All the cases I've studied,
Huh?
all the cases I've studied so far, whether epidemic or endemic, were within one country. So I haven't thought of that. But certainly there may be interesting cases. Typically, the Iraqi-Turkish question of the management of the EU practice, perhaps. It's a good suggestion. It's an interesting point. Because probably that's where you put it, you put it to test, whether something really big is safe, right? But certainly, large-scale water management plans in the future will have to include biodiversity protection. Do they do now? No. Certainly not. Can we ask why certain tools like the cell phones are not socially biased like one would imagine? The fact is you can track mobility because every time you make a phone call, the antenna, the provider, gets you the signal to. He is alerted. So essentially you know who called and where he was. If you move from antenna to antenna, you can track mobility on an unprecedented scales. So essentially, one of the things we have to do, and you say, okay, now it's only the rich that move in the Democratic Republic of Congo have a phone. No, it's not true. Of course, there are pockets in different places, South America, different things, etc. But it's an interesting thing in which you see our habits change because of a stupid phone that everybody carries, right? And the possibility where you have to use it for good. But now, try to get from a provider those data. You don't get them, those data. Why? Because they don't want to let you know where the antennas are. It's a commercial thing. But you say, what if I can predict disease? Because, you see, that was saying in the beginning, is the river network a template for the spreading of disease? Certain diseases, yes. River blindness, opistorchis, the diffusion of liver cancer, for instance, but you have, because of a certain fluke, it's called the liver fluke, that you get it if you eat fish raw, as we do in Laos in particular. The big thing is eating fish raw, those cyprids, fish, etc. It's the place which is like 100-fold more the incidence of liver cancer in that place. Now, these are the template for the spreading of disease where you can fish. They actually get the fish and eat it raw. But there are cases in which the infection spreads, and in the human mobility that it takes the pathways for the spread of the disease. And I would say that in most of the cases, well, even vector-borne diseases to a certain extent need water, but it's a different story. It's more complicated, like malaria. Let's confine attention to something which we can have attention. So what I'm saying is that what has been missing in epidemiological literature, or to some extent in the biodiversity literature, was something in which predictability, quantitative. What is engineering? I've been wondering, right? Engineering is computation, it's evaluation, it's predictive evaluation of something you can be tested, you can be evaluated, something you could be challenged for. Something we have to highlight the assumptions and the limits and the validity of the results. So I think what these guys need is really good engineers, like the one you guys trained at Purdue, I have to say.
Thank you. Thank you very much, Andrea.
Thank you so much.